Hello friends, so in today's class we are going to discuss about the electrostatic potential energy. So before starting electrostatic potential energy, what is the meaning of the potential energy? So we know that energy acquired by a body by virtue of its position is called potential energy. So potential energy is only defined for, only defined for conservative forces, only defined for conservative forces, conservative forces. Now question arises, what is the conservative force? So conservative force, in a short, we can tell that this is the force in which work done by this force depends on position. Work done by force, work done by this force, work done by force, work done by force, by force depends on position, depends on position, depends on position. So here we can understand that if it is depends on position, work done depends on position, and the definition of the potential energy is what? Energy acquired by virtue of position. It means there is a meaning of potential energy only for conservative force. For non-conservative force, there is no meaning of potential energy because work done by non-conservative forces depends on path. For example, if if the object moves from point A to point B, and it moves from point A to point B from different paths, path 1, path 2, path 3. And if it moves from different paths, then also if initial and final position is same, work done is same. If work done is same, W1 equals to W2 equals to W3, then this is the case of what? Conservative force. This is the case of conservative force. But if W1, work done by path 1, is not equals to work done by path 2, is not equals to work done by path 3, then this is the case of non-conservative force. Non-conservative forces. Non-conservative, non-conservative forces. Correct. So here example of conservative forces are what? All field forces. Here, all field forces are what? Conservative forces. All field forces. All field forces. Field forces means what? Like gravitation force. Field forces means what? Gravitation force. Gravitational force. Gravitational. Gravitational force. Electrostatic force. Electrostatic force. Electrostatic force. Same way, magnetic force. Magnetic force. So this type of forces are what? Field forces, and these are what? Conservative forces. With this, spring force is also example of what? Conservative force. Spring force is also example of what? Conservative forces. Correct. In non-conservative force, we have what? Friction. We have what? Friction. And any viscous force. Correct. This is example of non-conservative force in which work done doesn't depend on position. It depends on path. Correct. Now here we have to discuss the work done by the electrostatic force, and that work then stored in the form of potential energy. So here we are going to discuss about the electrostatic potential energy. Electrostatic potential energy. Electrostatic static potential energy. Potential energy. So basically, potential energy is what? The work done against the field, work done against the field stored in the form of what? Potential energy. So here, which field is there? Electric field is there. So work done against the electric field, any charge is doing that stored in the form of what? Electrostatic potential energy. Correct. So here, for example, capital Q charge is there. So its effect will be in its surrounding. Its effect means what? It's filled in its surrounding. Correct. So if capital Q is here, so its effect will be in its surrounding. Its effect means its field is there in its surrounding. Now, if I am bringing a small Q charge or a Q charge, another Q charge here, correct? in the field of this capital Q. Let it is at point P, and that is the distance of R. Correct? And initially I considered capital Q and small q is very far away, so that there is no interaction between capital Q and small q. Very far away, we considered it as an infinity. Correct? From there, if I am bringing this small q, let x is variable that is changing from infinity to R, then the work done against this field is stored in the form of potential energy. So here, when I am bringing, we have to the charge experiencing the force, electrostatic force it is experiencing, and here by doing external work done or external force, by applying external force, we are able to bring this charge in this field, and the amount of work done that is stored against the field of this charge is known to be as a electrostatic potential energy. Correct? So here, due to the external force, how much work done we have to do to bring this charge from infinity to this point P, that is at R distance from capital Q. So because this force is variable, so first we will find dW. So at any point where x is the distance, the force will be K capital Q small q by x square. And we know the work done is force or displacement. And as the external force and the displacement is in the same direction, so it is Fs cos 0 degree. So it is displacement is small displacement. Let we are doing small displacement here. Dx for small displacement work done is what? We can use Fs cos theta. So we have written kqqq by x square dx. Now to find the total work done, we have to integrate it. So W equals to integration of dW. Now it is what? K capital Q small q integration of what? X to the power minus 2 dx. Now x is changing from where to where? We are bringing from no interaction to a point in the field that is at R distance. So no interaction is at infinity. So from infinity to R. Correct? Okay. So now after integration, what we will get? Let's see. Here, K, Q, Q, and then x to the power minus 2 is there. So it will be x to the power minus 2 plus 1 divided by minus 2 plus 1. Integrating from infinity to R. Infinity to R. Correct? So it will be minus K, Q, Q. Then it is x to the power minus 1 R infinity. So minus K, Q, Q 1 by x. So finally, we'll get it minus K, Q, Q 1 by R minus 1 by infinity. This will be minus K, Q, Q by R. As here we are calculating the work done by external force, so here we will write U equals to minus W. That is what? Minus K, Q, Q by R equals to K, Q, Q by R. In some books, you will find it is directly written U equals to W. At that time, they are calculating work done by this electrostatic force, because the definition only tells it is the work done, potential is the work done by electrostatic force to bring a charge from Q to a point P in the field of the another charge. So that time you can directly write U equals to W. So here we get the interaction energy. This is also known to be as the interaction energy between the 2-point charges. Interaction energy between 2-point charges. Correct? This is what interaction energy between 2-point charges. If more than 2-point charges will be there, means multiple charges in the system, then how to find their interaction energy? We will see in the next slide. So interaction energy for the system of multiple charges, it means more than 2 charges. For example, if I will take one any triangle, let the charges are Q1, Q2, Q3, and the distance between these charges are R12, R13, R12, and R23. And we have to find the net interaction energy of the system of charges. So here first we have to see how many pairs are formed. So here total number of pairs are Q1, Q3, one pair, Q1, Q3, one pair, Q1, Q2, second pair, Q3, Q2, third pair. So any other possible pairs? No, only three pairs are there. So we will find the total interaction energy, U total of the system, U total of system is, U total of a system is K Q1 Q3, and the distance between R13, K Q1 Q3 by R13 plus next pair K Q1 Q2 by R12 plus K Q2 Q3 by R23. So this is what the interaction energy of what multiple charges, system of multiple charges. Similarly, one more example we'll see. For example, we have charges on the vertices of a rectangle. So let us consider the rectangle sides are A and B. This is also A and this is what B. And here charges are Q1, Q2, here Q3 and Q4. So again, as I discussed with you in the last case, we have to see how many pairs are possible. So Q1, Q2, one pair, Q2, Q3, another pair, Q3, Q4, another pair, Q1, Q4. So here four pairs you are seeing on the vertices. Is there any other pair? Yes. Diagonal pairs are also there, Q1, Q3, Q2, Q4. So total system interaction energy can be written as, K Q1, Q2. Distance between them is A plus K Q2, Q3. Distance between them is B plus K Q3, Q4, K Q3, Q4. Distance between them is A, K Q1, Q4 by B, and the diagonal pairs. Here, this distance can be written as A and B, then it will be root under A square plus B square. So it will be K Q1, Q3, K Q1, Q3 divided by root under A square plus B square. Similarly, another diagonal pair is Q2 and Q4. So K Q2, Q4 divided by distance between them is again root under A square plus B square. So this is what the potential energy of the system of charges. Now next one is closest distance approach for two charged particles. Closest distance approach for two charged particles. Whenever in the question you are finding the closest distance approach, in your mind two things must become. What is that? First one, conservation of energy. First one is what? Conservation of energy. Conservation of energy. And second one is what? Conservation of momentum. Conservation of momentum. Momentum. Correct. Now we will understand it. For example, in one case, if there are two charges, let Q1 and Q2, initially separated by a distance r, and Q1 is given a certain velocity v. Correct. Now in the question it's asking what is the closest distance of this system of charges. Here Q2 is fixed, means Q2 cannot move. So how close Q1 can come to Q2? So let it can come maximum R dash. So we have to find R dash value. So as I discussed with you, whenever there is a closest distance, first we have to think about the conservation of energy. So when we given certain speed v, what is the total energy initial? So here kinetic energy initial and interaction energy initial. So what is the kinetic energy initial? Because Here I consider the mass of the charged particles are m1 and m2. So half m1 v square. And here, because this is fixed, it will not move. So its kinetic energy 0. Next initial interaction energy is what? 0.2 point charges. So it can be written as k q1 q2. Initial distance is r divided by r. Now next one, let when the charge will come at this point, at point where the distance between them becomes r dash. So that time total energy final will be written as kinetic energy final plus interaction energy final. Now as the charge cannot move, go more nearer, it means the kinetic energy final will be 0 because its speed becomes 0. Then only it cannot go more nearer to Q2. So kinetic energy final will be 0. But there will be interaction energy due to Q1, Q2. That will be K Q1 Q2 divided by R dash. K Q1 Q2 divided by R dash. I'm writing again this one. Here you can write final kinetic energy is 0 plus K Q1 Q2 by R dash. Now by conservation of energy, by conservation of energy, by conservation of energy, we can write total energy final equals to total energy initial. So here total energy final is what? K Q1 Q2 by R dash. K Q1 Q2 by R dash equals to, it is half m1 v square, half m1 v square plus K Q1 Q2 by R. From here you can find the R dash value. So whenever there is a questions like this, we always think about the conservation of energy and we can solve the problem. Now next case is, here I considered that Q2 is fixed, but in the case when Q2 is not fixed, so what will happen? Just try to understand. So here in the case 2, for example, there is a charge Q1, correct? And charge Q2, it is not fixed. Here we given the speed, here we given the speed, here v1, and this one we given the speed v2. Let initial distances r, correct? Okay. So it is asking what is the final, for example, finally their nearest point with each other. That means closest distance they possible, they will be near to each other is r dash again, r dash. We have to find r dash value, correct? So let this time its velocity is v1 dash and its velocity is v2 dash, correct? Always keep it in mind that when the distance between them will be minimum, when v1 dash and v2 dash will be same, then only they cannot move, they cannot go more nearer to each other. The distance will be what? Closest one. So you can consider here the final speed will be same, then the closest distance will be. So here we can also write here, it will be v dash and v dash. It will be what? V dash and v dash, v dash and v dash. So here, what can we write? Here we can write, here v dash we have to find in terms of v1 and v2. So by conservation of momentum, by, as I told you that we have to think always two things, one conservation of momentum and conservation of energy. So here by conservation of momentum, conservation of momentum. So what is the total initial momentum? Total initial momentum is, here masses are m1 and m2. So it will be m1 v1 plus m2 v2. And what is the final momentum? m1 v dash plus m2 v dash, correct? Okay. So here we will use the conservation of momentum, means final momentum equals to initial momentum. And with this, we will find the V dash value. So V dash value will be m1 v1 plus m2 v2 divided by m1 plus m2. After getting V dash, we can use conservation of energy. So by conservation of energy, by conservation of energy, total initial energy equals to total final energy. So what is the total initial energy? Half m1 v1 square, half m1 v1 square plus half m2 v2 square plus k q1 q2 by r. Correct? Final energy half m1 v dash square plus half m2 v dash square plus k q1 q2 by r dash. V dash already we will find from here and we'll put the value here, and then we can find the r dash value also. So like this, in this type of questions, we can use always conservation of momentum or conservation of energy. By using that concept, we can find the closest distance approach. Correct? Now, here we will solve few questions based on the concept that we have studied. So here question is given, 2-point charges each of mass m and charge q are released when they are at distance r from each other. So here 2-point charges each of mass m and charge q. So each of mass m and charge q. Mass is m and charge is q. When they are at distance r from each other. Because they are same charge, so they will repel each other. Correct? So what is the speed of each charged particle when they are at distance 2r? So let they reach to position so that the distance between them becomes 2r. So in this type of cases, we always use the conservation of energy. So total energy initial equals to total energy final. So what is the initial energy? Because it is released, so initial kinetic energy is 0. Initial kinetic energy is 0. Kinetic energy initial is 0. What is the potential energy? Because they having interaction, so potential energy is k q square by r. K q1 q2, so q into q is k q square by r. Total energy final. So let their speed is v and v. How I got both these should be the same? You can use the conservation of momentum also. Their masses are same. So initial momentum, because they are in rest, it is 0. Final momentum m into v1 plus m into v2. So mm cancel. We are getting v1 equals to minus v2. It means the speed will be same in opposite direction. Correct? So that's why I directly took v and v. So here, final kinetic energy is always positive. So it will be half m v square plus half m v square. And because they are at distance 2r, they are in interaction with each other. So we can say their interaction energy will be k q1 q2 k q square divided by 2r. Correct? So here we will write it is k q square by r minus k q square by 2r equals to mv square. Correct? So finally, we are getting v square equals to k q square by 2mr. So v is root under k q square by 2mr. This is the answer of this question. I think so all of you understood this. Next question. Find the electrostatic interaction energy of the system of 4 charges placed at the vertices of a square of side A. So we will take a square, correct? And here, because there are 4 charges, and let us consider the charges are Q1, Q2, Q3, Q4, and the square of side length A, So here we can write the total interaction energy is number of pairs. So K, Q1, Q2 by A plus K Q2 Q3 by A plus K Q3 Q4 by A plus K Q1 Q4 by A. Correct? Correct. And diagonal charges pairs are also there. So it will be diagonal length is root 2A. So it will be K Q1 Q3. One diagonal is K Q1 Q3 divided by root 2A plus K Q2 Q4 divided by root 2. If it will be given the equal charges, then Q1, Q2 value, all values will be what Q only will put and we'll get the answer. Correct? I think so all of you understood this. We'll go for next question. Now it is given the three small balls of mass m and charge q are placed at the vertices of a equilateral triangle of side length L. So three small balls are there, each of mass m and charge q are placed at the vertices of a equilateral triangle of side length L. So here the side length is given L. Correct? Side length is L. Now what happens? The ball is released. So for example, if it is released, so this will, for example, this charge will experience the force due to Q in this direction. This charge will experience the force due to this in this direction. So net force will be in this direction. So it will move in this direction. Same way, this will move in this direction. This will move in this direction. Correct? So finally, what happens? The separation between the balls becomes 2L. So here, this charge is separation becomes 2L. Means charge will reach here, here, and here. The separation becomes what? 2L. Initial separation was what? L. Correct? Correct. Now the separation becomes what? Separation becomes 2L. Now what is asking here? Find the speed of the balls when the separation between ball becomes 2L. Same way, by conservation of energy. By conservation of energy. By conservation of energy. Always keep it in mind whenever it is released or speed something asking, always think about the conservation of energy. Correct? So initially it is released means total kinetic energy initially is 0. Kinetic energy initially is what? 0. Interaction energy will be there because there are three pairs. So K, each charge is same, KQ square by L, and three pairs are there. So directly I can multiply by 3 equals to kinetic energy final. So let their speed becomes V here. Each speed will be V because all the conditions are same. They're having same masses, same charges. So here we can say their speed will be V. So kinetic energy of each will be half mv square into 3 are there. So 3, correct. And their interaction energy will be what? K q square by the distance between them is 12 and they are 3. So 3, correct. From here you have to find the speed. So this 3 will take common, it will cancel out. Correct? Now kq square by L minus kq square by 2L is what? Kq square by 2L equals to half mv square. This 2 cancel out. So finally we will get, what will get V? V equals to what? V equals to kq square by ml root under kq square by ml root under kq square by ml. So like that, we can find the final speed of these charges. I hope all of you understood this lecture. We will continue in the next class. Thank you.